Hello everyone. So in this video, I'm going to talk a little bit about my project, which consists in studying theoretically the adsorption of hydrogen sulfide in two materials. One is the amorphous silica, also known as SBA, and the other one is the same material but doped with cobalt, which we're going to name as cobalt SBA. And the reason for that is because hydrogen sulfide is a pollutant gas that has to be removed due to environmental and health reasons. However, due to its properties, this gas can be transformed into hydrogen, which is a very sustainable fuel using the appropriate catalyst. And recently, it has been synthesized this appropriate catalyst, which is the cobalt SBA5. This catalyst has shown promising results. So in order to implement this catalyst in a bigger scale, we have to investigate certain things, being the adsorption process, the first step. And how do we investigate this? Well, we do it using quantum chemistry methods, specifically semi-empirical and density functional theory with a plane wave basis set. This means that we are using periodic conditions that are very appropriate to describing solids, like it's the case of these both materials. So how do we do it? First of all, we took the pristine SB structure from a previous work, and this is a quite big structure. It has more than 200 atoms, and this is because it's a amorphous nature. So we need a lot of atoms to be able to describe this amorphous nature. So now we are going to dope it, and we have to match the experimental 10% atomic ratio. So for that, we are going to take the 15 more external atoms, and we are going to replace 6 of them with cobalt. Now, this may sound a little easy. However, there are more than 500 combinations. So that's the reason we are using the semi-empirical method to to, to get the lowest energy structure in a qualitative way. And well, once we get the lowest energy structure of all that and possible combinations, we reoptimize this lowest energy structure, but now at the density functional theory level, using a cutoff energy of 800 electron volt and a cap-on grid of 3 times 3 times 1. And well, with that, we get the optimized cobalt SBA structure, which now has 6 cobalt atoms. Now, due to how we are going to calculate the adsorption energy, which is we take the catalyst, the lowest energy of the catalyst structure, the lowest energy of the hydrogen sulfide structure, and also the lowest energy of this system combined. I mean, the catalyst plus the adsorbate. But there are a lot of possible options to let's say, combine these both systems. So for that, we have to map the potential energy of the surface, and we are doing 256 single point calculations, and we also do this at the XTB level. And well, at the same level, we calculate the density of states at the density functional theory level. So these are the results. First of all, this is the pristine SBA structure, which, like I said, is taken from a previous work. And this is how the potential energy changes with the hydrogen sulfide position. And we can see that this is the cobalt SBA structure. And we can see that it's quite different, the potential energy surface. And well, the suitable sites for hydrogen sulfide to adsorb are the one with the lowest energy. And we can see that when we add cobalt, there are a lot of new lowest energy sites that are formed due to cobalt's addition. So this makes the structure more suitable to absorb the hydrogen sulfide. And this is the optimized cobalt structure. We can see that it has 6 CO atoms, well, cobalt atoms. And this is like the lowest energy structure that we obtain, like I mentioned to you on the methods. And this is the density of states plots. We can see that for the pristine SVA, it has a very, let's say, a very clear band gap of about 5 electron volts. And when we add the cobalt, we see that the d orbitals of the cobalt fall right into the band gap. So that gave us some insight about the d orbitals of the cobalt give more electron mobility, so that makes it more, let's say, more active and more active in the catalytic way. And also, this is the adsorption energy that we calculated, and we can see that for the pristine SVA, it is much more strong, the interaction between between the SVA and the hydrogen sulfide, unlike the doped system. And this might tell us that when let's say that with cobalt, we are reducing the strength of the interaction. So this, we know that for a catalytic reaction, we need to adsorb it and then desorb it. And maybe with the pristine SVA, the adsorption is too strong, and in a certain way, it deactivates the solid, while with the doped system, the adsorption is still a bit strong. Actually, these are both chemisorption values. However, for the cobalt is smaller, and that means that the adsorption is still strong, but not as strong. So it may leave the hydrogen sulfide to desorb, and that may help the catalytic activity. And this is what the conclusion says, like cobalt doping reduces the band gap and new adsorption sites appear, and the reduction of the adsorption energy might help the transformation to hydrogen. So, well, that's my work, and if you have any doubt or comment, this is my email, and I'll be glad to answer it. Thank you.